We're going to summarise our equilibrium changes and effects of changes on our equilibrium. So I have written an equilibrium equation up on the board. I would like you to tell me which direction it goes if I increase the temperature.
To the left.
I can't remember.
It's an exothermic
Why?
reaction to the left. Because an exothermic reaction can be considered as a backwards direction, make it more endothermic and take away the increased amount of heat.
Good. I would like you to do this in the exam.
Yeah.
Forward reaction is exo, which means the backwards reaction is
Exo?
no.
It says, see
How
what it
do you
says, like
know?
minus
See the
10.
way.
Oh, that's.
Because that's not negative 950 means that it
Does that mean, because is it negative
That's
because it
what
goes out
we
energy?
learned.
Oh,
yeah.
right.
reacts.
And
Yeah.
actually takes in. Why is exothermic cold if it takes in energy?
No. It loses heat to its surroundings.
No.
Not endo, sorry, I meant endo.
Yeah,
Why
you
is
said
it cold
endo.
if it's getting hotter?
No,
It's
it's not.
taking.
Because the surroundings are getting colder.
But
'Cause it's
see,
taking
if you
in.
dip your finger in an exothermic solution, is it warm?
Yes, we had this discussion. Okay, so yes, as someone said, you can actually write heat as a product on whatever side. If the backwards reaction was an exothermic, then you would write heat on the left hand side.
So it should go the way we don't have it. When not it.
Exactly.
Yeah.
Okay, what happens if I decrease my pressure?
You go to the left. No, decrease, go to the right.
Right.
Why is that?
There's more gas molecules in the right.
Great, love it. What happens if I decrease the temperature?
It's going to move to the right in order to replace the lost temperature.
Good. So
Excellent.
replace more heat. Yeah, so decrease in temperature favours the endothermic, or exothermic, sorry. What happens if I increase my concentration of water
Move
or
to the
steam?
left, move to the left.
Moves to the left to try and remove that steam. What happens if I increase my pressure?
It's going to move to the left
Why?
because there's less gas molecules in the left.
Good. And what happens finally if I increase my concentration of ammonia?
Goes to the right.
Goes to the right to try and remove that ammonia. Great.
So you
I'm
just go where there's less stuff. When you add it, it goes to the right where there's less of it.
yeah, to try and use that ammonia up and get rid of it. Yeah. Okay, so I wanted to check page 6 that we had everything written in, please.
So if you had a more O2, would it go to the right?
Yes.
Okay, so page 6 where it says summary of temperature changes. So the first case is for when the forward reaction is exothermic, so like we have on the board here. So an increase in temperature favours the what reaction? Endothermic. And so the equilibrium position moves to the left, and so that results in a what yield? Decreased. So that should say those gaps should be endothermic, left hand side decreased yield.
Are you doing this much yet?
Pardon?
Are you doing this yet?
Yeah. What? Oh,
Except
Yeah.
for my stuff, so I probably just watched it.
oh okay. And then what about an increase in temperature favours the
Exothermic.
exothermic reaction, and so the equilibrium position moves to the right in this case, and then that leads to an increased yield. Great. So the second case is then when the forward reaction is endothermic. So an increase in temperature still favours the
Left.
no, it still favours the which reaction?
Exothermic.
Endothermic, and so the equilibrium position moves to the
Left.
this case the forward reaction is endothermic,
To the right.
moves to the right hand side, and that has a result of what?
Right here.
Increased yield. Then if we, that should say, oh yeah, this is what we needed to change. That second bullet point should say a decrease in temperature.
On the top one as well.
Yeah, it is. A decrease in temperature favours the exothermic reaction, and so the equilibrium position moves to the
Left.
left-hand side, which has a result of decreased yield. But basically, as I said the other day, if you learn that an increase in temperature favours the endothermic change, then everything else is just the opposite. A decrease in temperature favours the exothermic, and then you can just work out whether your forward reaction is exo or endo. Okay, so just wanted to check that one catalyst we talked about. Your summary is there, and the bits in bold, kind of if you learn them, you should be sweet as long as you can apply it.
Carl's just nothing, don't it?
Yes.
Why did you do it?
Because it just affects the both equally.
I'm very impressed. Very impressed. Okay, let's have a look at industrial reactions. What's wrong with you?
Let's get no texture here.
Me?
Yeah.
Yeah.
What is
Oh, no, that's
the Haber-Bosch process?
It's like NH3 or something, isn't it?
How to make ammonia?
It's like 3N2 plus,
No, it's 2 and 2 plus 3H2 equals
and she's reversible, remember?
2 NH3.
That's you. You got 3 marks for that last year, it was so easy. It's 2
No.
NH3, miss.
It's 2NH3, but it's only 1 N2 on the left. You said 2 N2.
Sure.
Wait. I'm quite sure.
TCSA,
Quite sure.
In this session.
Alright, our enthalpy change for this reaction is minus. It's on the side of that. Yes. So have a little think. What are going to be our optimal conditions? What is wrong in terms of temperature and pressure?
Well, how are we meant to do?
Temperature
400
quite low,
atmosphere.
pressure quite high.
By 300 degrees.
Okay, yeah,
It's
I'm not
60
looking for
atmospheres,
specifics,
isn't it?
but like high, low
Or 200
temperature,
atmospheres.
pressure.
How do you know?
Or is that the contact process?
Have a think of your-
I don't know.
Think of your
Oh, she's
It's
actually
equilibrium.
GCSA is strong.
Okay, no, I
But
don't
she's
care
actually
about
directly
specific.
down on-
Okay, so it wants high pressure and low temperature.
Yeah.
Tell me why.
Because
actually-
low temperature will favour the exothermic route, which will increase yield,
Mhm.
moving the equilibrium to the right, and then increased pressure will also move equilibrium to the right and increase yield.
Because
Due to the Arrhenius principle.
because
Lower gas in the way, say, high pressure.
there's more gas molecules on the left, and so an increase in pressure, it moves to the side with lower gas molecules, because that has an effect of lowering the pressure of the
If you make it
system.
cooler, it gets hotter. Ask Echo.
No, if you make it colder, it stays the same temperature because the reaction itself gets hotter in order to balance out the change
Oh,
in
but
temperature.
it does actually get hotter in a sense per se. The overall thing doesn't get hotter, but
No.
the right side gets hotter. To cancel out the left side.
No, the reaction itself gets
Yeah,
hotter to balance out the
That's so
decrease in
technically though, how does it get
temperature.
hotter if it's colder?
No, don't think of it that way.
Does it?
No.
Don't-
It's like-
definitely
it's
don't
like
think of
you-
that.
See when you get cold, your body starts to shiver
Yeah,
to react more per se to heat up.
So
But
we say
your body temperature stays the same temperature. Your body's just like
yeah, it doesn't do anything.
doing more work in order to
Yeah,
keep it the same.
okay. So we've got low temperature and a high pressure. What is going to be the problem with that?
It's hard to do both.
Pardon? Not necessarily.
Don't know.
Your products will be water liquid.
Liquid, okay, that's a possibility, yeah, but not likely. We're not likely to freeze it, like, we're not.
Freezing, so you said liquid, that's solid.
Yeah, I know. We're not likely to put it at less than 0. Ammonia's boiling point is probably minus 100 and something.
Should be a gas on it.
Or no, sorry, nitrogen's. Nitrogen's boiling point is what? Minus 190 something.
At low temperatures, it's not like because of it's going to be a low rate then. Nothing.
Bingo. So low temperature.
Oh, you just bucket away
And-
catalyst, don't you?
At low temperature, it's going to be a very low rate. So yes, what we have is constantly a battle between our equilibrium and our rate. So yes, a low temperature will favour our equilibrium, but it's not going to favour our rate. Our reaction is going to be really, really slow. And so what we need to do is find a compromise. Call this the battle between kinetics, which is your rate, and thermodynamics, which is your equilibrium.
Compensation point if you will.
Yeah. So we're gonna look for a compromise. So if you flick to the back page, the compromise is so it says there, Aristoteli's principle suggests low temperature, high pressure. But compromise is that we use a temperature of 450 degrees C.
It's not really hot.
It's pretty hot, but not like super hot. You could use like 900 or thousands of degrees.
What would it be if you weren't compromising?
Low
Like
temperature. Well, yeah, or room temperature. Or, yeah, and a pressure of 250 atmospheres, which is pretty high. But then to help this, we've got a catalyst. So that's our compromise. Our compromise is 450 degrees C, 250 atmospheres, and an iron catalyst. That is all there, but I would like you to sort of just underneath it write conditions. Oh,
You're just gonna throw in like a block of iron.
well,
Like, how do you actually get that to like catalyze stuff? Or does it just kind of do it?
just kind of does it. What did we say? Our catalysts like to have a
Flat. I don't know what you're doing here. Like,
Small surface, large surface area.
yes, yeah. So remember we talked about finely divided. Catalysts are finely divided.
Is that for like everything? I thought it was finally divided now.
Well, no, in general, catalysts are better
Oh,
when
yes,
they're
yes,
finely
yes,
divided
yes,
because it's all about surface reactions. Okay, so I'd like you just underneath to write conditions and then just list them kind of in bullet point form.
so you just like sprinkle in some like iron powder.
Yeah. 450 degrees, 250 atmospheres. Josh, you're not even on the right page.
I don't know what the right is.
I said turn to the back page. Okay, did you learn about the process of forming sulfuric acid?
Yes.
Contact process.
I'm sorry, I didn't pick up on that.
That's okay.
Right.
We're going to move on to that now,
Is that just talking
and that
about
is called contact process. Contact process, and this is how we make sulfuric acid from sulfur. Sulfur dioxide is one of the steps, and that's the one we're going to focus on.
steps?
This is the one that uses
Sulfur
the
dioxide
He's just scanning through all the chemicals.
reacting with sulfur, or reacting with oxygen to give us sulfur trioxide. We need to put in a couple of balancing numbers here. These are all gases.
He's got an error. Unexpected out of the bag area there.
It's taken away too soon.
Okay, please again, could you tell me what my favourable conditions are going to be?
Flavorable.
Favourable.
Low temperature and high pressure.
Why is that, Ronan?
Explain this 4 times.
And you'll be able to explain it now in your module 2.
The temperatures because it's more. Was this for the contact process?
Yeah.
Oh, I'm wrong.
Oh.
More right than the
Oh,
left
right.
side. But basically, there's less gas molecules on the right hand side, so increased pressure will favour the right hand side of the reaction.
Yep.
And then increased temperature will cause the reaction equilibrium to move to the right, to the left.
To the left.
It's a
Oh.
decrease in temperature,
It's a decrease
so
in
it'll move to
temperature.
the right in order to be more thermal change.
Think about it.
Okay, so our forward reaction is exo. We can tell that from our
You said an increased temperature would do that?
negative
We're
sign.
right, but we're wrong. The right answer for the wrong question.
So yes, again, we want a low temperature and a high pressure.
Do you know like S plus O4 or something there? Or 2O2?
No, this is just one of the steps of the whole process.
First step, like.
I know, all I was saying at that stage was it's getting sulfuric acid, which is H2SO4 from sulfur.
But you know, like pieces of
I know, it's not an equation. I asked you what you were making your sulfuric acid from. Okay, so what is our problem with a low temperature and a high pressure?
Slow
Slow
reaction.
rate of reaction.
Slow as, okay? And, yes, so,
Is there
again, we
anything
need a
with the catalyst
compromise.
itself?
What?
Is there anything with the catalyst itself? Like it catalyzes itself? That'd be so good. 'cause then it's like makes
Human
itself quicker.
reactions?
Yeah, what?
And,
Any reaction.
no, like, in your body? Is there not stuff in, oh no, but then it doesn't catalyze
As you
itself.
make more of it, it just gets quicker. It'd be so good.
Oh no, because catalyst is something that's not used up. Substance that speeds up the reaction, but it's not used up itself, so it wouldn't be
Like
a...
nuclear fission.
How do you stop a reaction? How do you stop a catalyst reacting then?
When there's no products for it to help react. It doesn't react, it just speeds up the rate of
No, that's
reaction.
how do you stop it? Reaction?
Okay, anyway.
If
block it up
there's
again.
nothing there for it to catalyze, then it won't catalyze.
Anyway.
What enzymes?
Yeah, and enzymes are catalyzed. Is it?
Oh, that's
Yes.
bad. Yeah.
It's bad
So
off.
we need to again compromise. So we wanted a low temperature, but it's going to be really slow. And so we want a slightly higher temperature, but we also need to be careful. There it says, however, at high temperatures the sulfur dioxide liquefies. I think that needs to be low temperatures. So low temperatures, the sulfur dioxide liquefies, and then it's a liquid, and it's not much use in a reaction. And also the rate is too slow, so we've got two problems there. Not only is the rate too slow, but also the sulfur dioxide is going to liquefy. And so we need a compromise again, because at higher temperatures the rate's better. Right, so in this case, our compromise conditions are 450 degrees C. What do you notice about that temperature?
It's the same as the other one.
Good, yeah, so you kind of probably look at these thinking, there's so many conditions to learn, but if you can try and remember that they're both the same, 450 degrees C. It's 2 atmospheres, and our catalyst is V2O5.
Is that vanadium oxide or pentoxide?
Yeah.
One should zero down to
Okay, and there's also a cool thing with this. Our conversion is 95%. It's very, very good. But also, this is, what type of reaction is this?
Exothermic.
Exothermic. And so it gives out heat itself, right? So what we're saying is that we want to use a reasonably high temperature to get the rate at a reasonable rate, okay? But there's a problem with the high temperatures. If it gets too high, because it's exothermic, it's going to, if we heat it up and then it's exothermic, it's giving out even more heat. That's going to have effect of what on my yield?
Decrease.
It's going to decrease my yield. So we want to keep it around 450 degrees. We don't want it to get too much higher than that, because that's going to decrease our yield. And so actually this reaction releases enough heat as it is to, if we use the excess heat that's generated in the reaction to heat the reactant gases, so my sulfur dioxide and my oxygen coming in, then that's enough heat to sort of maintain it on 450 degrees C. We don't need to add any extra heat. Okay, so if we added any extra heat, our temperature would rocket high and our yield would be very low. So that's the point of the last little sentence, is that we don't need to even add any extra heat.
Cool.
Finito.